Well, at the start, the last speaker this morning, Professor Dietmar Salamon from Zürich. This is the title of the talk. You can go first. So please.
Okay, thank you very much for the kind invitation. It's a great pleasure to be back here in Madrid, and especially at this honorable occasion. And I think we met first when way back when I was still at Warwick and you were a PhD student in Oxford. And well, in between, some of our students had some contact with each other. I mean, that's another interesting anecdote, which I'm going to skip over. I think Ignazi will remember it. Where is he? He's not here yet. Okay. So, and then we met again at the Pacific Rim Conference in China, not far from Shanghai, in 2016. And that was very nice. And we discovered that we had some mathematical interests in common, and it started some collaboration on the Ricci form as a moment map and related stuff. And this, what I'm talking about today, is kind of vaguely related, loosely related to what we worked on. So the subject is infinite dimensional analogues of geometric invariant theory, and I want to begin with a recap of the finite dimensional story. And I understand there are many people here who know this stuff much better than I do. So, but I will ignore those. And beginning with a closed Kähler manifold on which a compact Lie group acts, and the algebraic geometers among us, they will not like this notation because a compact Lie group is called K and not G. But for me, it's called G. And so we have a group action on by Kähler isometries on our manifold, and the infinitesimal action assigns to every element of the psi of the Lie algebra vector field V psi, and the hypothesis is that this vector field is a Hamiltonian vector field generated by a Hamiltonian function which can be assumed to depend linearly on psi. And also this notation should I will use throughout that Alex psi is the vector field V psi at the point X. So, so this means that H psi is the inner product of mu with psi, where mu is some map from X to the dual of the Lie algebra that generates this action. And the hypothesis is that that H psi is a Hamiltonian function for the vector field V psi is exactly this equation 1. And now the other hypothesis is that the moment map is equivariant, and that's essentially for for connected groups equivalent to this second equation. And in this situation, one can form a very interesting quotient by taking the zero set of the moment map and dividing by the group G, and which, at least in certain favorable cases, is a nice symplectic manifold. So because we have a Kähler manifold, it is now interesting to complexify the group, and this complexified group is uniquely characterized by a certain universality property. First of all, its Lie algebra is a complexification of the Lie algebra of the original compact group. And secondly, if it contains the group G, and if we have any other complex Lie group and a homomorphism from G, or compact group, to the complex Lie group, then it extends uniquely to the complexified holomorphic homomorphism from the complexified group GC. And so this, by definition, determines a complexified group uniquely up to isomorphism. And an interesting example that one can use here is that the group G is the automorphisms of our manifold, Kähler manifold X that preserve the group J, that's a finite dimensional complex Lie group, and then follows immediately the complexified group acts holomorphically on our Kähler manifold. And in that case, one would like to look at the complex quotient, and that's the subject of geometric invariant theory, to study such complex quotients, and that in general is a kind of bad space. It's typically not even Hausdorff. And so to obtain a nice quotient, one chooses a suitable subspace of our Kähler manifold X. And so one such choice of subset is the space of polystable points where the complexified group orbit, which no longer preserves the symplectic form, the complexified group, so where the complexified group orbit intersects the zero set of the moment map. And then it follows essentially from the definitions that this quotient is actually at least bijective and actually isomorphic to the symplectic quotient. And but the space of polystable points is kind of not so nice a space. It is not open in particular in general. And so one replaces, in algebraic geometry, they replace it by the space of semi-stable points, where only the closure of the complexified group orbit intersects the zero set of the moment map. And then one gets the same quotient if one chooses a correspondingly larger equivalence relation. And then one gets a space that's equal to the symplectic quotient. And this observation goes actually back to Mumford. And one of the key questions that one addresses in geometric invariant theory, which are the points of X that participate in the construction of this complex quotient? So which are the semi-stable elements of the manifold X? How can one characterize the stability condition? And the key ingredient from my point of view, and which goes back to the work of Mumford, is the so-called Mumford weights that can be assigned to a point X and an element of the Lie, a non-zero element of the Lie algebra. And it is this number where one considers the complexified action of psi on X and takes the limit as t goes to infinity and takes the evaluation of the moment map on psi. And these numbers, these Mumford weights, they satisfy an interesting inequality. Namely, if we take any such Mumford weight and normalize it by the norm of psi, then a minus the weight divided by the norm of psi gives a lower bound for the moment map on the complexified group orbit. So what this inequality shows is that if you have any negative weight, then the lower bound must be positive. And so therefore, the point must be unstable. The closure of the complexified group orbit cannot intersect the zero set of the moment map. So it gives an instability criterion. And conversely, if the right-hand side is positive in finite dimensions, one actually gets equality. So the converse is true as well. And a corollary of this is the Hilbert-Mumford criterion that a point is unstable, i.e. not semi-stable, if and only if there exists a negative weight, or conversely, a point is semi-stable if and only if all the Mumford weights are bigger than or equal to 0. So now, a key ingredient in proving all these assertions, especially in establishing the moment weight inequality, is the Kempf-Ness function. So one considers this this homogeneous space GC mod G, and this is a Hadamard manifold with negative curvature for the standard metric arising from the choice of an inner product on the Lie algebra that is also already needed for the moment weight inequality. And then the moment map gives rise to a natural function on this complexified space GC that is essentially defined by its derivative. So one can show that this moment map for each given point x in our Kähler manifold, the right-hand side of this equation defines a one form on GC, and this one form is closed, and furthermore, the way it is defined, we can integrate it over GC mod G, which is a constructible space, and then get a well-defined function. And this GC mod G is a Hadamard space. It is connected, simply connected, non-positive sectional curvature, and this functional phi x is convex along geodesics. So one can use this these convex functions on the Hadamard spaces to prove these basic statements like the moment weight inequality, and to characterize stability. And also the geometric meaning of these Mumford weights is that if you consider the function, this Kempf-Ness function on the Hadamard space in the direction of a geodesic ray, then the slope at infinity is precisely the weight W mu of x psi. And so intuitively that makes clear that if the weights are all positive, the function phi x should be bounded below, and that characterizes semi-stability. And this is then the flow of the gradient flow of the Kempf-Ness function can then be used to establish all these basic facts. And it is closely related to the negative gradient flow of the moment map squared, which is another interesting ingredient in the story, which I'm going to skip over here. So now the main the subject I want to go into is a certain specific infinite dimensional analog of this picture, where our Kähler manifold X is replaced by a certain infinite dimensional Kähler manifold. So, and that subject arises from considering almost complex structures on a closed symplectic manifold. So let's fix a closed symplectic manifold M omega with a volume form rho, and consider the space of all almost complex structures that are compatible with omega. Now this space can be viewed as a space of sections of a fiber bundle over our manifold M, where the fiber at each point x is the Siegel upper half space associated to omega and j at the point x. And that's a Kähler manifold. And so the space of sections of a bundle of Kähler manifolds is a kind of infinite dimensional Kähler manifold. And one can write down explicitly, the tangent space of derivative of a path of complex, almost complex structures is a complex antilinear endomorphism, and the compatibility condition for the tangent space translates into this complex antilinear endomorphism being self-adjoint. And then one can write down explicit formulas for the symplectic form. So if you take two infinitesimal almost complex structures, J1 hat and J2 hat, then you take the trace of the product J1 hat J, J2 hat, and integrate that over M against our volume form. And then that formula gives you a symplectic form, standard symplectic form essentially, on the fibers integrated over our manifold. And the complex structure is just multiplying J hat with J. That preserves the self-adjoint condition and the complex antilinearity condition. And the only thing is that with these choices of signs, this standard complex structure will be compatible with minus the symplectic form on the previous line. So now, in this situation, one has the group of Hamiltonian symplectomorphisms acting on the space of almost complex structures and preserving both the symplectic form that's written here and the complex structure. And a theorem by going back to Quinn, Fujiki, and Dawson is asserts that this action of the Hamiltonian symplectomorphisms on the space of compatible almost complex structures is a Hamiltonian group action, and that the moment map, so it should be a map which goes from the space of almost the complex structures to the Lie algebra, or the dual of the Lie algebra of the space of Hamiltonian group of Hamiltonian symplectomorphisms. Now, the Lie algebra is a space of functions, or the functions modulo R. So you can think of the dual as a Lie algebra of the Lie algebra as a space of functions of mean value 0. And so what the moment map does, it assigns to every J the scalar curvature of omega and J minus the mean value of the scalar curvature, which is just a topological invariant. So, and that's the point of overlap with our work with Oscar, is that the definition of the scalar curvature involves the Ricci form by this formula that you take the 2 times the Ricci form, you wedge it with omega to the n-1 over n-1 factorial, and then you divide by the volume form. And so it's not exactly the scalar curvature of the Riemannian metric determined by omega and J, but it's some modification of it. So in this case, the moment map identities that we have in the finite dimension setting carry directly over to this infinite dimension situation, where the this S omega hat that shows up here is understood as a derivative. So S omega hat of J hat is by definition the derivative at t equal to 0 of S omega JT, where J0 is J and d by dt Jt at t equal to 0 is our J hat. And so the precise equivalent of the moment map identity in the finite dimension setting is just exactly this formula, equation 4, where on the left-hand side, the Lie derivative of J in the direction of the Hamiltonian vector field VH is denoted by LVHJ. And it is given by this formula written there. And also this moment map is evidently equivariant, and that leads to the second formula here, that if we take the symplectic form and plug in 2 such Lie derivatives, we get a pairing of the moment map, i.e. the scalar curvature, with the Poisson bracket, which is the Lie algebra, the Lie bracket on the space of functions for the Lie algebra of the Hamiltonian group. So now in this is just the moment map picture, and then the question one would ask is, what about the other parts of infinite dimension of finite dimensional GIT. What becomes of the GC? What about the complexified group? What about GC mod G? What about the Kempf-Ness function? Do we have all of these? And the answer is that actually we don't have a complexified group. And nevertheless, there is a natural analog of the space GC mod G in the integrable case. And this analogy that was basically noted by Donaldson that led to a big program in the constant scalar curvature Kähler geometry. So the first few things are exactly what I just explained, that the moment map is given by the scalar curvature. The moment map squared evidently is a Calabi functional on the space of J's, and one can look at the gradient flow just exactly as in the finite dimensional situation. But now to go beyond that and to obtain an analog of GC mod G, one needs to restrict to the integrable case. And then one gets the so-called Futaki invariants, which are the analogs of the Mumford weights. There's a notion of stability which goes back to Yau, Tian, and then Donaldson of K-stability, which is the equivalent of polystability. And the space GC mod G becomes the space of Kähler potentials. And that's a very interesting space. GC mod G you can think of as a negative curvature manifold that is dual to the Lie group G. And here, the space of Kähler potentials plays such a role. These are other symplectic forms in the same cohomology class that are still compatible with omega. And any such cohomology class can be written in this form, omega h plus half of d, dh composed with j. And this space has its tangent space, again, the space of functions, just like the group of Hamiltonian symplectomorphisms, but it becomes a negative curvature manifold, which has been studied by Calabi and Shushang Chen and Mabuchi and others. And the analog of the Kempf-Ness function is then the Mabuchi functional on the space of Kähler potentials. And the Kempf-Ness flow, which is a negative gradient flow of the Kempf-Ness functional, is its equivalent is the Calabi flow on the space of Kähler potentials. And the Hilbert-Mumford criterion, the analog of it becomes the Yau-Tian-Donaldson conjecture, which was then proved in the Fano case by Chen, Donaldson, and Son about 8-9 years ago. So this analogy, the second half of this page, only applies to the integrable case. And the question I want to discuss in the rest of this talk is, what can one do in the non-integrable case? What if J becomes non-integrable? Can one find an analog of the space of Kähler potentials? Can one find a manifold that is a symmetric space of negative curvature? Can one find a functional that is convex along geodesics on the space? And can one then get to analogs of the moment weight inequality and of the Hilbert-Mumford criterion in this situation? So that's what I want to address in the second half of this talk, what one can possibly do to carry the story over to almost complex structures. So, well, the starting point is, as I mentioned before, the Lie algebra of the Hamiltonian group is just a group of functions, let's say with mean value 0. That's why the rho is there all functions that have mean value 0 with respect to rho. And so complexifying the Lie algebra is easy. We just take the complex valued functions with a complex Poisson bracket. And then the trouble is that this, for this complexified Lie algebra, there is no complexified group. So that's why this construction of GC, that doesn't work for the group of Hamiltonian symplectomorphisms. However, what one can do is consider the infinitesimal action of the group of complex valued functions on the space of almost complex structures. And namely, all one needs to do is to take the two functions f and g, and for f we take the usual action by the Lie derivative, and for g we take the action by the Lie derivative and multiply it with a complex structure, hit it with a complex structure, and then leads naturally to this operator Lj. And that would be the infinitesimal action of the group of the Lie algebra of complex valued functions on the space of almost complex structures. And that leads to a definition of a complexified group orbit. And the suggestion would be to call two almost complex structures exact isotopic if they are related by a path that is tangent to this infinitesimal action at each point t. So you can think of the image of Lj as a set of all infinitesimal almost complex structures that have the form LVFJ plus J L VGJ over all F plus IG as a kind of subspace of the tangent bundle of J of M omega, a subbundle of the tangent bundle, and that is an involutive subbundle. And so what one might expect is that one has a kind of Frobenius theorem that tells us that we have leaves that are tangent to this foliation, and the equivalence relation would exactly be the solutions of equation 6. So that's where the definition of exact isotopy comes from. And it is obviously an equivalence relation on the space, and we denote the equivalence class of an element J by GC of J, hinting that GC of J should be something like the complexified group orbit of J. So now this equation 6 is a very innocent looking equation, but it seems to be a very complicated one. The way it's written, it hides the difficulties. So for example, if you prescribe f and g, there's absolutely not a well-posed initial value problem. You can easily write down examples of functions f and g, especially g. For f is no problem, but you can write down a function g so that with initial condition j0 equal to j, there is no solution on any time interval. And even uniqueness seems to be an open problem. At least the PDE people I talked to so far didn't know offhand an answer to this question. And this would lead me to make 3 conjectures about this equation. Let me write it down again. So dt jt is L EFT JT plus JT L GT JT. So that's the most important equation of today's lecture. And the first conjecture is a uniqueness conjecture for the solutions, that if you prescribe the functions ft plus IGT and you prescribe the initial condition for J, then at most you can have one solution. And in fact, the uniqueness conjecture in the full formulation is not just for this nonlinear equation, but it's for a corresponding linearized equation. And so there's a class of linear equations for which this uniqueness should hold. I'm confident that this is true, but I don't know how deep into PDE theory it goes to prove that. So I should also say that I can prove uniqueness with a fairly easy argument if this f is 0 and g is independent of t. But if g becomes depending on t, then that proof doesn't work. So I don't know the answer. And then the other is the existence conjecture. Why? For given f and g, you cannot expect any existence result. But what should be true is that if you prescribe the value of the function g for t equal to 0 and the initial condition, then you can find a path gt for which a solution exists. And that is certainly true in the integrable case. With the help of the space of Kähler potentials, one can prove that. And then the third conjecture relates to the kernel of this operator Lj. And let me point out that if you take Lj star Lj, then you have a Fredholm operator. It's a fourth order Fredholm operator on the space of complex valued functions. And so therefore its kernel of the kernel of Lj must be finite dimensional. And this Gj is actually a finite dimensional Lie algebra with a complex Poisson bracket. And the third conjecture is that the dimension is constant on each equivalence class of J's. So again, this conjecture is easily seen to be true if you consider the integrable case. So under these three conjectures, I propose that the space of Kähler potentials can be generalized and extended to the almost complex setting. And the key to understanding this is the theorem, is a kind of Frobenius type theorem for this subbundle of this tangent bundle of almost complex structures. And so what does the Frobenius theorem say? Essentially, it says if you have two parameters S and T, and you assume you have a path that's tangent to your subbundle at S equal to 0 in the T direction, and that is tangent to the subbundle in the S direction, then in all vertical directions, this path is also tangent to the subbundle. That's the essence of the Frobenius theorem. And this theorem 1 says that under the assumption of the uniqueness and dimension hypothesis, this infinite dimensional version of the Frobenius theorem is true in the present situation. So in other words, if in the S direction, the derivative of J is given by this operator Lj with functions V and G, then there exist also functions H and K, so that in the vertical direction, the derivative of J is given by the same formula, also tangent to the subbundle, and that furthermore, the relation between the functions f plus ig and h plus ik is given by this identity that's written here. So, and a corollary of this that one gets immediately by choosing J, F, G independent of the T variable is that the initial condition would then be belong to the Lie algebra G, to the kernel of this operator L, that the one gets that the Lie algebras Gj and Gj prime for exact isotropic pair not only have the same dimension, but actually are isomorphic as complex Lie algebras. So that's a direct consequence of this theorem. And then now I propose if we make an extra assumption that, namely that our Lie algebra Gj0 is trivial. So that corresponds in GIT theory to the case that the isotropy subgroup is trivial. So this Gj0, that would be the Lie algebra of the isotropy subgroup in geometric invariant theory. So, and then also that the Hamiltonian group acts freely on the complexified group orbit. That seems to be not such a difficult condition because it's actually, I don't think any example is known where Gj0 is 0 and Ham does not act freely on the complexified group orbit. So in this situation, one can consider the quotient space of the complexified group orbit by the Hamiltonian group. That would be in the finite dimension setting, the quotient of the complexified group orbit by G. Instead of GC mod G, one takes the group orbit mod G. And this, the tangent space of this is then just the space, the image of Lj modulo the action, infinitesimal action of the Hamiltonian group, which is LVFJ. So this LVFJ disappears, and one is left with JLVGJ. So this means this quotient space has its tangent as its tangent space, again, the space of functions of mean value 0. And this is isomorphic to the tangent space of this quotient manifold by assigning to every function G the equivalence class of the infinitesimal almost complex structure JLVG. J.
Is that a space?
Yeah?
Is that a space H negatively curved?
That is then theorem 2. Right. So first we need the Riemannian metric, and all the natural choice of a Riemannian metric is to identify the tangent space with a space of functions and take the L2 norm of the function. So that makes this into an infinite dimensional Riemannian manifold. And now we come to your answer to your question. It's an infinite dimensional symmetric space with non-positive sectional curvature. So this would be the analog of the space GC mod G. And so what one finds is that a curve T goes to JT is geodesic if and only if it satisfies the usual equation that's written there, and if dt gt plus the Poisson bracket of ft and gt is 0. So that also is a hint as to what the Levi-Civita connection would be on this quotient manifold. And then one gets a formula for the Riemann curvature tensor that's very much similar to what one gets on the Lie group Ham of M omega itself, namely the triple Lie bracket is the curvature tensor, only that in this case there's no minus sign, and that means that if one writes down the sectional curvature, one gets something negative. Of the plane spanned by V1 and V2, one gets minus the integral, the L2 norm squared of the Poisson bracket of G1 and G2, which should correspond to these vectors V1 and V2. And then the third theorem is that one gets a generalized Mabuchi functional. So if one just in a straightforward manner carries over the definition of the Kempf-Ness function to this infinite dimensional situation, which Mabuchi did in the in the integrable case. Then one would get this formula, and then the observation is that with the help of theorem 1, again, this functional that one gets here is first of all well defined, and that it's also convex along geodesics. And well, I prepared a slide here for the proof why it is well defined, and I don't really want to go into this. What is going on here, that all the equations that appear in theorem 1 and in the moment map in the Quillen-Fujiki-Donaldson theorem, all these equations flow into proving that this functional is well defined. So in particular, to go from the first equation, just the definition of the Mabuchi functional, going from the first to the second, is the equation 8 that appeared in the analog of the Frobenius theorem. And then one can use some integration by parts for dsk, and one gets, using the other equations, one gets all these cancellations, for which then show that this function is well defined. So don't want to dwell on this here. And with the help of all the story, one would, at least in a certain special situation where the Lie algebra is trivial, the Lie algebra, the kernel of Lj, where this thing is 0, if this Lie algebra is trivial, at least one would get the ingredients that one has in the integrable case, namely an analog of the space of Kähler potentials, an analog of the Mabuchi functional, and one could ask the corresponding question then, for example, is there a moment weight inequality? So, so that would be this question. If we take an arbitrary almost complex structure and any Hamiltonian function of mean value 0, then let us assume that the equation, which is essentially that equation written over there, equation 6, but with f equal to 0 and with g independent of t, so gt always equal to h. So suppose that this equation has a solution for all time. That would then correspond to a geodesic ray in the space of Kähler potentials. And then if you write down the analog of the Mumford weight, you get exactly the term that's written here on the left-hand side. And the question would be, is this term less than or equal than the infimum of the moment map on the complexified group orbit? So that would be the precise analog of the moment weight inequality in this infinite dimensional setting. And this inequality that is known in the integral case by work of Shushong Chen and Simon Donaldson. And in this situation, it is an open question. And then the next question might be if the Hilbert-Mumford criterion also carries over in this situation, namely the infimum that it's positive if and only if this limit here, which is the analog of the Futaki invariant in this infinite dimensional situation, in this non-integrable case, if this limit is negative for some h. And the third question would be same question as in the integral case, under which condition can one find an element J prime in the complexified group orbit that has constant scalar curvature. So let's see, I have two more slides that I want to briefly discuss, in which I want to briefly discuss why this way of constructing the version in analog of the space of scalar potentials in the almost complex setting might be a reasonable one that, at least in the integrable case, also gives the right answer. And so the first thing, what one can do is return back to our equation 6 that's written there on the blackboard, and then use ft, gt, and jt to define an isotopy, psi t, that satisfies this equation, dt psi t plus vft plus jt v gt composed with psi t equal to 0, starting at the identity, and then pull all the structures that we have back by psi t. So then you get the pullback of omega is then a symplectic form depending on t, the pullback called omega t prime, and pullback jt, you get jt prime, and pullback gt by psi t, you get another family of functions which are called ht. And then this triple satisfies the following equations, 13, namely dt omega t prime is just d dh t circ jt prime. So that's is just a calculation. And dt jt prime is moving by the Neuenhaus tensor. So you get n jt prime of dot vt prime, and the vt prime is just the Hamiltonian vector field of ht for omega t prime. So this is an equation you get for when you do this pullback construction. And now the first obvious observation is that if jt happens to be integrable for all t, then the Neuenhaus tensor is of course 0, and therefore jt prime is constant, and so it's always equal to j. So jt prime doesn't move at all. You can forget about the second and third equation, and you just get the first equation, which is dt omega t prime is d dh t composed with j, and then that's just a path in the space of scalar potentials. So this translates this equation back into the space of scalar potentials. And then you can look at the geodesic equation. If you start from a geodesic, then the functions ht satisfy this equation, dth plus the norm of ht squared, omega t prime jt prime, by this metric is 0. And that's just the Monge-Ampere equation. And so if you, particularly if you have jt prime equal to j, the integrable case, then it's just the standard equation for geodesics in the space of scalar potentials. So you return to the situation that is familiar in the integrable case, the familiar equation for geodesics. And then the same thing happens with the Calabi flow, which corresponds to taking f equal to 0 and g being minus the scalar curvature, and then h is also minus the scalar curvature of omega t prime and jt prime, or j in the integral case, and that's the standard formula for the Calabi flow. So this means that the geodesics in the space really do correspond to the standard Monge-Ampere equation in the integrable situation. All right. So that's one indication why this might be the right direction to go into. And the second indication is coming from construction of Donaldson in the integrable case. So let's assume that J is integrable. And let's also assume for simplicity that H1, the first Betti number, is 0. And then this Lie algebra GJ, which I also always consider is the kernel of this LJ. Yeah? So this finite dimensional Lie algebra is actually, in this situation, isomorphic to the space of holomorphic vector fields, to the Lie algebra of holomorphic vector fields. And in this situation, Donaldson considers the space of pairs psi comma h, where h is a Kähler potential normalized, and psi is a diffeomorphism isotopic to an identity that pulls back omega h to omega. That such a psi exists is a direct consequence of Moser isotopy. And in this case, it is easy to show that, assuming always a uniqueness conjecture, yeah, that J prime is exact isotopic to J if and only if there is such a pair psi h, so that psi star J is J prime. So the Donaldson space Xj can be used to characterize the exact isotopy class of J. That's the first observation. And then the second observation is the construction slightly more general, because here I'm not assuming that Gj is trivial. So if Gj is non-trivial, then you get a Lie algebra bundle over the space of over the exact isotopy class of J. For each J prime, you have a Lie algebra Gj prime, which in this integral case happens to be the space of holomorphic vector fields. And then you can consider this space of all kind of the frame bundle of this Lie algebra bundle, which is a space of all pairs where J prime is in GC of J, and A prime is a Lie algebra isomorphism from Gj to Gj prime. And that's a kind of frame bundle. And this would be, I think, the right way of defining the space of Kähler potentials in this more general situation by taking Pj and dividing by the Hamiltonian group. And an indication why this is the case that is under suitable hypotheses, like that automorphisms of J, which are isotopic to the identity, this J should not be there, which are isotopic to the identity, is the same as those automorphisms that among automorphisms of J are isotopic to the identity. And if also this is also isomorphic to the automorphisms of the Lie algebra, which is at least true in some cases, then the natural map from Xj to Pj that is given by pulling back J and then using the pullback as the isomorphism from Gj to G psi star J. This map is then bijective under some fairly reasonable assumptions. So, and here for Xj, it is directly, if you take the connected component of the standard basis element, then Xj modulo the Hamiltonian group is actually the space of Kähler potentials. And so Pj modulo hem is also the space of Kähler potentials in this special case. And that might be motivation for exploring this further and trying to understand these various conjectures for the non-integrable case. Thank you.
Questions, comments?
Thank you for your talk. In the integrable case, the Yao-Tian-Donaldson conjecture is, of course, a manifold version of the Hitchin-Kobayashi correspondence relating Hermitian-Yang-Mills with the stability of holomorphic bundles over a Kähler manifold.
Yes, but where the gauge group is replaced by the diffeomorphism group.
That's right. Now, but in that situation, There is actually a non-interval version of that was studied by the Bartholomews and Tian. Right?
In the
Young-Mills, Hermitian Young-Mills.
In the Young-Mills situation.
I wonder
yes.
if you can extract any interesting thing from there. I mean, it's of course much easier problem than this, right? But
because the gauge, you have the gauge group instead of.
That's right. But it's a non-integrable situation.
Yeah, no, I haven't looked at that. Right.
Maybe interesting.
Interesting. Okay.
Steve?
Hi. So you said that in your infinite dimensional situation, you have the analog of the compact group, but there's no complex group.
No complexified
So
group, right.
Is the situation that nobody has figured out what it should be, or there's some reason why you know there cannot be?
Yeah, I haven't explored this question of actually proving that it cannot exist for some specific reasons. But even if you consider the two-sphere, right? So then the complexified Lie algebra is actually all vector fields. Every vector field is a sum of a Hamiltonian and the gradient vector field, right? And so you do have a Lie group, right? The diffeomorphism group, or diff0, right? But it's the wrong Lie bracket. Because the Lie bracket of the vector fields is not the same as the complex Poisson bracket. So the candidate for what you think might be the complexified group is actually not in the precise sense a complexified group.
So again, in the
Even though you do have a Lie group whose Lie algebra is isomorphic to F plus IG, to the space of F plus IGs, but not with the same Lie bracket.
So again, in the integrable case, the geodesics have a relatively weak regularity in general.
Yeah.
C11
I didn't get into that. Yeah,
So-
the theorem of Chan.
Yeah, exactly. So here, I guess you wouldn't expect better, but there's also F and G. So what kind of regularity? I'm a little bit confused what.
Well,
functions F-
the geodesics are here solutions of the equation BT-GT plus FT Poisson bracket GT is equal to 0. So I haven't even mentioned this problem. That is, of course, the key ingredient in Chan's proof of the moment weight inequality in the integral case is that he can prove that 2 points in the space of Kähler potential are joined by a weak C11 geodesic. And that, of course, here is an open question. And as you say, you don't expect better than that. And I mean, first of all, one needs the three conjectures to even properly define the equivalence of the space of Kähler potentials. And then one can start addressing this kind of question. And then also, I mean, there's all this beautiful work by Berman and Berndsen, where they prove that the Mabuchi function is actually convex along the weak geodesics and so on. And all that plays a key ingredient, plays a key role in extending the finite dimensional GIT picture to this infinite dimensional situation.
Okay, some more questions? Yes, please, Jürgen.
I just wondered if you know an obstruction to the existence of equation 6 there.
Yeah. If you ignore this term, right? If you put F equal to 0 and put G independent of T, right? And suppose you have a solution of this equation. And then you take in the S direction the flow of the vector field V, the Hamiltonian flow of G, and pull everything back by the Hamiltonian flow of G, then you get a holomorphic curve in S and T. For each P, JST of P will be a holomorphic curve in SNT. And and that directly gives you an obstruction because you can choose the Hamiltonian function so that the flow for some point P cannot give you the real part, the restriction of a holomorphic curve to the real axis. So that's very easy to construct counterexamples where you cannot have solutions. And that's also the proof, by the way, that solutions are unique in the case where G is independent of T and F is 0. Right? Or more general, solutions are unique for geodesics. That's the consequence of that.
Yeah. But that's assuming that ft is 0.
Yeah, that's assuming that ft is 0. But this problem is not a problem at all because you can also always pull back by the Hamiltonian isotopy of ft to get rid of this term altogether, and that also shows you can be used. Is related to this equation for geodesics.
But so does that mean you understand completely the obstruction?
Sorry?
Does that mean you understand completely what the obstruction to the existence is?
No, only if this GT is, if FT is 0 and GT is independent of T, then I understand. But maybe if you could understand that in general, when let's say F is 0 and G depends on T, then you could also settle the uniqueness problem, I suspect.
Thanks.
More comments? Well, let's thank the speaker again.
Thank you.